All right, so I think we're going here. We're going to just jump back in to start out with some more hypothesis testing examples today, where we left off. We'll do some by hand, and then we'll kind of transition into Excel. So we'll get a couple examples in Excel as well, where I'll kind of switch from Excel and show you what it would look like if we did those by hand as well. So we'll get a lot more examples of that. We'll just continue the discussion about hypothesis testing. Like I said, just going through more examples and kind of hearing this several times, I think is really going to be helpful. So go to where we left off last week. We were dealing with, we're dealing with examples where we were looking at the proportion, but just kind of in more general, whether or not we're looking at where the true population mean is, where the true population proportion is. We had the p-value approach, which, these steps, no matter what approach we take, are going to be the same, the first two. Figure out what our null and alternative hypothesis are. Specify the level of alpha we want to test against, and we can do several of those, but we'll usually just focus on one. We'll then calculate our test statistic or our z-statistic, right, telling us how many standard deviations away from the assumed true value we are. Once we have that test statistic, we can then, using what type of tailed test we have, find the p-value. If our p-value is less than alpha, we can reject, or we can do the critical value approach, which starts out the same, except for one of the, we can calculate our test statistic, but then we use alpha and the type of test we have to find a critical value, right? If our test statistic or our z-statistic is in our rejection region, using that critical value, then we reject. So we can do this two ways, right? So each one of these examples, I'll make sure I show you what it would look like no matter which approach we use, right? So for this first example that we're going to work through, let's say you want to test against the hypothesis that less than 15% of Indiana mothers smoked while pregnant. So going back to that data set we looked at a while ago. Now, one key difference here is, and typically I won't ask questions like this, but if you're looking at your homework, which after class today, I will assign one more homework kind of prior to this exam. It's going to be on Connect, and it's really just hypothesis testing problems. So it's just me making sure you're working through a lot of problems leading up into that exam, because that's going to be a good portion of the exam, and I want to make sure you're pretty familiar with how to do these hypothesis tests. So if we want to test against a hypothesis, that's what we said is the null. Typically what we say is, what do I want to test for? What do I want to try to find? And then I stack the deck against myself. But this terminology of what do I want to test against, right? Well, whatever I assume is true, that's what I'm testing against. So here, we're thinking about this, we're being told is the null hypothesis, that the true proportion is less than 15% or 0.15. So our null hypothesis is that it's less than 0.15. We always include the equality on that null. So less than or equal to 0.15, which means the alternative hypothesis is just the complement of that, which is that the proportion is greater than 0.15. So we've got what type of tailed test here? We determine the type of tailed test we have by the alternative hypothesis. So here I've got a greater than sign, so greater than or right tailed test. Think about this. If I've got the null is that the true population proportion is less than or equal to 0.15, any sample proportion I see less than 0.15 supports the null. So the only evidence I can find that I would reject the null with is sample proportion values to the right of 0.15, right? So right-tailed test or greater than test. We find the sample proportion of 0.18. We could find our test statistic or we could find our critical value. Those two are kind of, we could interchange those. So what we're really looking at here is I've got my distribution of sample proportions that assumed true population proportion that I was using was 0.15. I found a sample proportion of 0.18. Okay? So if we do the critical value approach first, what I want to do is say, look, I know I can convert that sample proportion into a z-statistic or into my test statistic. If I plot that test statistic against the critical values, I can make my rejection decision. So before we calculate the test statistic, let's get our critical values up there. So what we want with our critical values, and we could do this, the kind of nice thing about the critical values is they're always going to be the same. We're dealing with that standard normal distribution. So I'm going to actually look up 3, right? We could just test against one of those, but I'm going to test against 3 just to kind of show you, no matter which one we had, we could do this. So the first one I'm going to want to find, and I don't actually technically know where this is plotted yet, so I guess I shouldn't know that yet. So I want the critical value that gives me alpha, and for a right tail test, gives me alpha in that right tail. The first alpha we're going to find, let's try to do 0.1. Okay? So I go to my standard normal tables. So you got my Z tables here. We'll rotate them here. I want the area in that upper right tail, right, to be 0.1. Now the problem is the table always gives me the area to the left. So there's 2 ways I can do this. The first is I could say, well, look, if I want 0.1 in that upper right tail, what would the area be to the left of that critical value? Yeah, area under the curve is 1, so 0.9. Or, you could think about it, what we really did was 1 minus alpha. Now there's another way I could have done this. If I just looked up 0.1, I'm going to find the exact same value, but negative. So if I wanted to, I could just look up alpha and remember, oh yeah, it's a right-tailed test. For right-tailed tests, I'm always going to be looking at critical values on the right side of the distribution. And remember, my standard normal distribution is centered at 0. So for a right-tailed test, I can say, well, I could look up alpha, and just remember, it's going to give me the critical value I want, but negative, so I could just make it positive, right? So we can do it either one of those ways, and I'll show you both. So let's say we do, let's say we look up that area to the left of 0.9. Let's say we did it that way first. So go down here. Closest thing to 0.9, looks like it's in between these 2 values. So a Z value of 1.28 or 1.29, take the higher of the 2. So 1.29 there is what we're going to think about as our critical value. Okay? Now I could have looked up 0.1, just looked up alpha. If I look up 0.1, looks like I'm in between these 2 values. So negative 1.28 and negative 1.29. Take the higher of the absolute value, negative 1.29. But then remember, oh yeah, if I just look up alpha, right, it's going to give me the area to the left being alpha. It's going to give me the same critical value I want, but it's going to be negative. I just want that value to be positive. Sure enough, negative 1.29 would have just been 1.29, which is what we would have found if we had looked up the area of kind of 0.9 to the left of that. So there's 2 ways of doing that. This one, kind of looking up 0.9, is probably technically more correct. But if you're very comfortable with the idea that this distribution is symmetric and that you're looking up the same area to the left that you wanted on the right, then that's fine, right? You can just look up alpha and remember, oh yeah, it's a right-tailed test, it has to be positive. So we've got this critical value. We can do the exact same thing. Instead of an alpha of 0.1, what if we wanted an alpha of 0.05? And we could find that critical value. That would give me 0.05 in the upper right tail. So I could go through the same process. I could either just look up alpha and remember, oh yeah, it's going to give me the negative critical value, but it's a right tail test. Or I could look up not 0.05, but 0.95, right? So I could go ahead and do this, right, for 0.05, and I look up 0.05 in between these 2 values, so negative 1.64 and negative 1.65. Remember, we're dealing with a right-tailed test, so I actually want that value but positive. So my critical value there would be 1.65. So I've got, just to kind of clean this up a little bit. I had that critical value of 1.29. That corresponded to an alpha of 0.1. Got my critical value of 1.65. That corresponded to an alpha of 0.05. And I could do the exact same thing, but do for an alpha of 0.01. Right? I'm not going to walk through that one. It's the same exact process, but we look up 0.01. If we do that, well, give myself a little more room here so I can kind of believe we'll find 2.33, and that's for an alpha of 0.01. So I have my 3 critical values for 3 different alphas. My rejection region for a right-tailed test, wherever we find our critical value, draw the rejection region will be for a right-tailed test, the area to the right, left-tailed test, area to the left, 2-tailed test, kind of the area to the right of the positive critical value, area to the left of the negative critical value. So another way I said you could remember this, just draw arrows kind of into your tail, right? And that's your rejection region. Okay? Well, now what we need to do is say, okay, where will this 0.18 fall kind of on the number line, right? So we have to calculate the test statistic for the sample proportion we saw of 0.18. So we had a formula for this. Our test statistic formula for proportions was take the sample proportion, subtract the assumed true proportion, divide by the square root of the assumed true proportion, times 1 minus the assumed true proportion, divided by our sample size, where this denominator simply represented the standard deviation of our sample proportions. So we could go ahead and calculate this first and then just plug that value in, or we can do the formula all at one time, right? We've got our sample proportion of 0.18, assumed true proportion of 0.15, and our sample size of, I think it was 72. I forget what we were told in the problem there. So I go here. What was it? Yep, 72. Or no. 72 of 400. So our sample size is 400 here. Right? Excuse me. So let's go ahead. We have that equation. Oops, there we go. We plug everything in. We get about 1.68. Okay? So 1.68. So I do this a little bit out of scale because I didn't really know what the test statistic was ahead of time. Actually, I'm going to switch to the screen here in just a second. I'm going to use a different color here. So we've got our test statistic, 1.68. So we turn our sample proportion into this test statistic of 1.68. So it would be plotted just to the right of that critical value. Right? So we can see here, what levels can we reject the null at? Well, we found sample evidence that was in the rejection region, right? It's in that rejection region for an alpha of 0.1. So at the 10% significance level, I could reject the null. It's just barely in the rejection region, but still in the region for that critical value of 1.65, which corresponded to the alpha of 0.05. So we can reject at the 10 and 5% significance levels. But if we look at the alpha of 0.01 or the significance level of 1%, we're not in that rejection region with our test statistic, or with our z statistic. So we can reject the null here with 10 at the 10 and 5% significance levels, but not the 1%. Right? Or said differently, remember we said those significance levels, we could turn into confidence levels, where I can reject with 90 and 95% confidence, but not with 99% confidence. Okay? Any questions on anything there? How I went through a step too quick, or even if I have to go back a little bit. You okay with that? Okay. So, excuse me. If instead I wanted to have used the p-value approach, right, what I would have done is say, well, look, I have a right-tailed test. I want the probability that I saw sample evidence that went against the null that was as far away from that assumed true value as the sample proportion I found, or anything even further away. Well, I can't find that if I just have this normal distribution very easily, unless I want to do a bunch of calculus. But if I can convert that into a z statistic, or my test statistic, well, I can look up that z statistic of 1.68, and the area to the right of it, right, that would represent my p-value. So I could look up 1.68 on my table. Now the table will tell me the area to the left of that z statistic. I want the area to the right. So whatever area gives me to the left, I would have to subtract it from 1. So I'll go to my standard normal table, maybe in a second. There we go. I look up that Z statistic of 1.68. So 1.6, go over 1.68, 0.9535, okay? So 0.9535, but that's not the area I wanted, right? I wanted the area to the right of that Z statistic. So I subtract that from 1, right? Which gives me, let me see if I can, how much room I got here. I'll write it up here. Which gives me a p-value of, what, 0.0465? Okay. Now, if I use the p-value approach, in my rejection decision, I'm not worried about critical values and where my test statistic lies. I'm just looking at that p-value and I say, well, look, is that less than my alpha? If it is, I reject. If not, I fail to reject. Okay? So, is that p-value of 0.0465 less than an alpha of 0.1? Yeah, right? So, at that level, I can reject. Is 0.0465 less than an alpha of 0.05? Well, just barely, but sure enough, I can still reject. And is that p-value less than an alpha of 0.01? It's not. So there we would say I failed to reject, which is the exact same decisions I made down here, right? I kind of ended last class kind of drawing that comparison. Like, you know, if we do the critical value approach, we're really just comparing these Z values. And we do the p-value approach, we're just comparing the areas to the right of the Z values for a right-tailed test. Now notice, we just barely rejected at the 5% significance level here, and we just barely rejected at the 5% significance level using the critical value approach. Both ways would lead us to the same decision, right? It's really just looking at kind of two different axes here. Like, we're either comparing the x-axis values, or you can almost think about it as you're comparing y-axis values, right? But either way, we're going to get the same decision. And you don't have to do both of them, right? This is like a way more work than you'd ever have to do for one problem if you're just asked, do you want to reject it, right? Because you only have to use one of these approaches. You only have to use the p-value approach, or you only have to use the critical value approach. And usually, we're not testing against 3 different alpha levels. Typically, we're just looking at 1. Right? But if we were asked, which of these levels can I reject at, we could easily do that. Once we have the p-value, right, it's not that much more work to check against 3 different alpha values as it was to compare to 1. Okay? Any questions? Yeah.
I get where we got the 1.68, but when you checked your Z-score, how did you know the 0.08? Sorry, it was like 5 minutes ago. It was when you looked at your Z-score after the critical values, I'm pretty sure.
Oh, how did I get this?
No, I know how we got 1.68.
Okay.
But when you went to the Z-score and you were like on 1.6, I didn't
Oh.
know.
When I went to the table?
Yeah.
So we go to that Z-score, right? So we go to 1.6 and then over to 8, because that's our second decimal. So 1.68, right? Those, excuse me, those column headings represent our second decimal. Yep. So 1.68, and the probability to the left of that was 0.9535. One of the areas to the right. Yep. And then we count it from there. Any other questions on that? Okay with that? So this was a pretty extensive, I just wanted to kind of a little bit of almost review of both the approaches and kind of really show how much we really could do with just one problem. So hopefully that was a pretty comprehensive example. Kind of already made our rejection decisions here. I then have some slides in here that match up to what we're going to do in Excel. This third one, we haven't went over these problems yet. This will be next class. So for today, just slides 9 and 10. Next class, we'll kind of review how we do Excel work for examples where we don't have a population variance. We only have a sample variance, which you can imagine, just like confidence intervals, when we only had a sample variance, we had to use the student t distribution. So things will be a little bit different there. We'll wait and do that next class. For today, we're going to do some Excel work. So let me make sure. I think if we look here under files, and we go to in-class data, we've got hypothesis testing and hypothesis testing example tuition. We're going to just do this hypothesis testing one. And I didn't want to upload it ahead of time, but I'm going to do it right now, just in case if you want to work along from a blank, oh, where was it? I dragged and dropped it in here at the start of class. Here it is. You can start with that blank file if you want to. Eventually, with the work that we do in class, this blank file will eventually become this hypothesis testing that has all the answers in it. But, you know, if you just look at that and you don't see how it was built, you're like, what the hell's going on here, right? So let's start with that blank file, okay? Since we've been using proportion examples to start class, we'll just start with a proportion example, okay? So the idea that I had for this one, right, was let's say we want to test for whether the hypothesis, the population proportion of students who have tried e-cigarettes is greater than 25%. So I had this data set. There's a survey of like all these high school, middle school students and whether or not they've ever tried or smoked e-cigarettes. And we know, is the true population proportion greater than 25%, right? Or greater than 0.25 as a proportion, right? So that's what we want to test for. So we can think about really what we have here. Whoops. We're going to build this example up. Is we want to test for whether or not the proportion is greater than 0.25. So what we're going to assume is that that population proportion is less than or equal to 0.25, right? This is what we want to define, so we stack the deck against ourselves. Right? So what type of tail test do we have here? Well, we have a greater than sign in the alternative hypothesis, so we have another right tail test. So this is going to look very similar to the example that we just worked through in terms of the procedures, but we're going to see how we do it in Excel. Okay? So I've got my assumed true value up here, or hypothesized true value, HT is what I called it. And I'll zoom in so we can actually see what's going on. What did I do there? Oh, I wanted to make it huge. There we go. So if I want to find a sample proportion, and I have this variable which is 1 if the student ever tried e-cigarettes, 0 if not, we said that finding the mean, or simply using the average function in Excel of that 1, 0 variable, will give us our sample proportion. It'll count up the number of people who have ever tried an e-cigarette and divide it by the total number of observations that are in this data. So Control Shift or Command Shift on a Mac, hit that down arrow, hit enter, you get about 0.33. Now I put in a sample size here that's definitely, I have a much larger sample size here. I did this for a reason. I want to start out assuming I had found that sample proportion from a sample size of 100. We'll then look at, well, what if I actually use the entire sample? Like what if but I need to make a point with this. So I put that 100 in there for a reason. So we've got that right-tailed test. Let's say we want to do this test at a 90% confidence level, okay? So my alpha here would be 0.1, okay? So my test statistic, this is really just going to be, we're just going to use Excel to be a calculator, right? We're going to put in that function that we had earlier, right? This guy right here. We're just going to type that into Excel, but select the cells that have these values in them. Okay? So our sample proportion minus the assumed true proportion, divided by the square root of the assumed true proportion times 1 minus that, and then divide by our sample size. So in Excel, we're going to take our sample proportion, subtract the assumed true sample proportion over here. Right? And I put that in parentheses because that's what's going to be in our numerator. We then want to divide that by the square root of that assumed true proportion times 1 minus that assumed true proportion. And then we divide that by our sample size right here. Okay? So it's a lot easier, especially when we're doing these proportions and trying to enter this into Excel, because how far do I keep my sample proportion? To the second decimal, fourth, fifth decimal point. Here I can just click on the cell and it puts in the exact value for me. Okay? So this should give me my test statistic. Right? Now before I hit enter here, My assumed true value is 0.25. I found a sample portion of 0.33. So if I think about, and I'll go back to Excel here in just a second. So I think about what I'm looking at here. The assumed true value is 0.25. I found a sample proportion of about 0.33. If I turn this into a z-value, what do I know has to be true about the sign of this z-value, or this z statistic? It's going to be greater than a certain value. I think someone said it's greater than 0, right? It has to be positive because it's to the right of that assumed true proportion, or that kind of mean of our distribution. So remember, this mean of our original distribution should have a z-score always of 0. So if we find sample evidence to the right of it, our z-statistic will be positive. If we find sample evidence to the left of it, our z-score will always be negative. Now, this may not seem like, this can just help us from making like easy mistakes. For instance, if I hit enter here, oops, enter here, so I get my test statistic. What if I had forgotten these parentheses? I'm going to get a negative value because it's not doing the order of operations right, and I'll go, whoa, I know I did something wrong here, right? Like, if I just drew this out and plotted that sample portion against the assumed true, I know I have to have a positive test statistic, right? So I go back, oh, I forgot my parentheses, right? Okay? Any questions on up to this point? All right, that's pretty good. So what if I want to find my p-value? Well, remember, our p-value for a right-tailed test is going to be the area to the right of that sample proportion that we found, or the sample statistic we found. Now, typically, we would turn this into a z-value, then look up that z-value or that z-statistic in the table. The table tells me the area to the left, so I would have to subtract that from 1 to get the area I wanted, which was the area to the right. Well, we can do that in Excel. If we want to function in Excel that works just like we were going to go to the table to look up a z-value, we have that norm.s.dist function, right? It says take a standard normal distribution, look up this z-value. Well, the z-value I want to look up is my z-statistic or my test statistic, comma, we always put a 1 there, and it gives me the area to the left of it. Right? Now here for a right-tailed test, I didn't want the area to the left of my z or my test statistic. I wanted the area to the right, so what's the only other thing I need to do? Just put 1 minus there in the front. Right? So it's going to look up from the table the area to the left of 2.02797, then subtract it from 1, and return to me my p-value. Okay? Or the probability I saw this z-statistic or this test statistic or anything further away from that assumed true population proportion. Okay? Any questions on that? Okay with that? So it's really just like we were doing it by hand, but instead of using the table, now we can use that norm.s.dist function. Right? Now here before, I'll do the p-value approach, and then I'll show you the critical value approach in Excel as well. So one thing that we haven't done yet, a couple people I think have Google searched and used this not necessarily in cases they needed to, but I'm going to show you how to use this if function in Excel. Right? And we don't have to do this, necessarily, but I'll show you why it is kind of useful if we started to want to change the different values we wanted to hypothesize, or assume that the population proportion is equal to, if we want to change our alpha value. So let's use that if statement. The very first thing we tell it is what we want to test to see if it's true, right? So what I'm going to do is I want to say, okay, if my p-value is less than my alpha value here, right, then I want to reject, right? I know that's what I want. That's the p-value approach. If the p-value is less than alpha, I reject. So if that is true, the first, I put a comma. The next thing I will tell this if function in Excel is, what do I want to put in this cell if this statement is true? So if the p-value is less than alpha, I want to put the word reject in there. Now, if I want to put words essentially in Excel, or non-numeric values, I have to put them in quotation marks. So I'm going to say, look, check to see if the p-value is less than alpha, If that is true, if it is in fact less than alpha, put the word reject there because I know I want to reject the null if that's true. Comma, if it's not true, I want to put fail to reject in this cell. All right? So the if statement, you first put what you want to check to see if it's true. Next thing is, if it is true, what do you want the cell to show? Third and final thing, if it's not true, what do you want to put in, what do you want to show in that cell? Okay? So if I hit enter here, what word should I see? Reject, right? Because my p-value of 0.02 is less than the alpha of 0.1, right? So I hit enter here. Sure enough, I see the word reject. Right? Now, what if I put in an alpha of 0.05? Should I still be rejecting? See a couple head nods, right? So 0.05, right? My p-value of 0.02 is still less than that, so I still reject. What if I want to go down to the 1% significance or the 99% confidence level? Is my p-value less than the alpha of 0.01? No, so hopefully when I hit enter here, I see the word fail to reject. Sure enough, I do. Right? And so this way I could test against several different alpha values and get my rejection decision very easily. Okay? Any questions on that? You want to see that cell again, or okay with this? Okay. All right, what if I instead had decided to use the critical value approach? Well, I still need my test statistic, right? I still need that z statistic. But now I want to find the value, right? I want to find that critical value that would give me, when we look at critical values, we're looking at that standard normal distribution. So I want the value that gives me my alpha of 0.1 in that right tail. Now, when we did this by hand, we found that this was 1.29, well, approximately, right? We can get more exact in Excel, but the problem is when we use the function in Excel, it works just like the tables. And what we will do is we'll tell Excel the area to the left. So if I want the area to the right of 0.1, the area to the left would be, we said earlier, 0.9 or 1 minus whatever alpha I want in that upper right tail. So when we go to Excel, for my critical value, instead of the norm.s.dist, I'm working backwards, right? I now know the probability I want, and I want to find the value that gives me that probability or that area in the tail. So I'm using that inverse, right? Norm.s.inv. I'm working backwards, right, or inverse. Okay? So all that function needs is the area I want in that left tail. Well, we said I know that I want alpha here. I changed it. I'll change it back to 0.1, but I wanted 0.1 in that upper right tail, so I had to do 1 minus whatever area I wanted in that upper right tail because I need the area. I need to tell Excel the area to the left. Right? Okay. So just 1 minus that alpha value. I'll go back and change this to 0.1 because that's what it originally was. Sure enough, we get a value that's in between 1.28 and 1.29. We had to estimate it, right? Or we had to kind of round it to, or use the higher the value, so we used 1.29. But here we can get the exact kind of z value that would give us 0.1 in that upper right tail. Now, if we had forgotten that we're dealing with a right tail test and we simply looked up alpha, what value should I get? We just found what, 1.2155 or something? So if I only looked up alpha and I forgot to subtract it from 1, it's a symmetric distribution, right? So I should find that same value, but negative, right? That's why the critical values for a left-tailed test are the exact same as the critical values for a right-tailed test. It's just that the left-tailed test, the critical values are negative. Right-tailed test, they'd be positive. So let's go back in and fix that to make sure that it's what we actually want, which was the right-tailed test. Now, if I hadn't done the p-value approach, I could have used that if statement to do a very similar thing to make my rejection decision, right? Because here, once I find this critical value, I only reject if my test statistic or my z statistic is somewhere in this rejection region, right? This area to the right of my critical value. So if I have a test statistic that's greater than my critical value for a right tail test, then I would reject. Right? So I can go to Excel and say, well, look, I have those two things. I have the critical value, I have the test statistic or the z-statistic. So if that test statistic or z-statistic is greater than my critical value, it would be in that rejection region. So I'll put the word reject, whoops, I can type the word reject. If that doesn't hold, I'll put the word fail to reject. Very similar to what we did with the p-value approach, just now we're not comparing the p-value to alpha, we're comparing the critical value to the test statistic. Okay. So if I hit enter here, I should hopefully get the exact same rejection decisions that I had in that p-value cell. Okay. Sure enough, I reject here. We said that 0.05, right? Looking at that p-value, we didn't reject. And notice when I change this, because I was using that cell reference for alpha, it updates my critical value as well. And if I change this to 0.01, well, now we fail to reject, right? And you could go through all the alphas. These will never be different, right? We have this set up correctly. If they ever end up being different, you made a mistake somewhere, because they should always be the same decision, okay? And you don't have to do both of these. Once again, I'm not going to give you another Excel assignment prior to this upcoming exam, but we might do some hypothesis testing stuff afterwards. So this is all going to be relevant probably to kind of work you might have to do in Excel after the exam. But once again, I don't constrict you on the exam. If you want to use Excel to do some of your hypothesis testing, you can, right? So that's why I'm kind of showing you how to do it now, okay? Yeah. This one? Oh, yeah. Okay. Any other questions on that before we keep moving? Yeah. No. Whatever you put in here, it's just what you want. If I didn't want to be so emphatic, I could have just put the word reject, right? Or, well, I guess I have to choose one that we would have reject. Right? I don't know, just to make it easier to see and kind of, you know. That's not a silly question at all, because I'm sure there's some functions in Excel where you do have to put things in all caps for it to recognize it. So that's not, no. All right. So one thing I wanted to point out here, and why I put this sample size of 100, is because with a sample size of 100, if we wanted to be able to say this with what, 99% confidence, or an alpha 0.01, that's where we were failing to reject, right? So, you know, sample size of 100 is relatively large. The sample proportion I found is pretty far away from that assumed true value, and I still can't reject it, right? So when we're dealing with proportions, I think I mentioned this with confidence intervals, it's really hard to like narrow down the range with confidence intervals. Same idea, it's kind of harder to make rejections when we're dealing with proportions. But notice, if I actually use that count function, and I use my entire sample, which was much larger than 100, right? I had like 19,000 people here. Well, if I can get a really large sample from like a survey, well, now notice my p-value here is almost 0, right? And so I'm rejecting with ease. In fact, not only can I reject that the true proportion is less than or equal to 0.25 based off my sample, once I have like this really large sample, I can start to like really narrow it down. Well, what about 0.3? Right? Still easily rejecting. What about 0.31? Whoops, if I put it in the right cell, 0.31. Still easily rejecting. What about 0.32? Still easily rejecting. Can I say it's actually greater than a third of people? 0.33? Not quite, right? With 99% confidence, you know, kind of one of the last values I can reject is that 0.32, right? Yeah. Oh, let's see if I can get that again. There we go. So anytime I see this e to the negative, I should be thinking this is like the scientific kind of format. So I could change the format of this cell, and it would show me it would move the decimal point 8 places to the left. So 0.00000007. Anytime you see this e to the negative, you pretty much know that's 0, right? Like that's so close to 0 that even, you know, it could show us 6 or 7 decimals. It doesn't have a value. It's still 0 all the way out to the 6th or 7th decimal, right? Now, if you do something like you narrow the range, you might start to get like e to the -1, which really means it moves at one place. So then you got to be careful. But yeah, when you've got a cell that's a normal kind of width, in order to see that scientific format, it's going to have to be really small value. Yep, that's a good question. So just in case people listening or kind of if you're watching the video, the question was, what does this e, what does this mean? And it means move the decimal 8 places, and it's negative, so to the left. Okay? So pretty much 0. So we can, with large samples, we can start to make rejection decisions that there's almost no way, even when we found sample evidence that was pretty inconsistent with what we assume to be true with a smaller sample, with smaller sample sizes here for proportions, it's just really hard to be able to reject certain values unless we saw like a sample proportion really far away from this. So let's say I saw a sample proportion of 0.5. Well, yeah, then I can start to reject things because I'm so far away from that assumed true value. But for the most part, right, it helps having kind of a larger sample size. Okay? Any questions on that one? All right, that's pretty good. We're going to kind of take a step back and look at examples where we're looking at a mean when we know the population variance. So somehow we know the population variance here, right? So I believe the way I had this one set up on the slide is we have this BMI data, and we say, okay, look, let's test for whether or not the true mean BMI in the US is less than 30. We'll assume it's greater than or equal to 30, right? We got this huge data set. So we have a left-tail test now. Okay. So left-tail tests are actually quite a bit easier. So we think about our left-tail test, and now we have a sample mean. We distribute it around that value that comes from our null alternative hypothesis of 30. I think, and I'll show you in a second, but we find, I believe it's 29.5 as our sample mean approximately. Well, now the p-value for a left-tailed test we can think about is the area to the left of that sample evidence we found. Okay. So we'll go to that Excel document. We're now dealing with I was given the population variance. Here I'd already calculated the sample size for you. Hopefully we're familiar. It's just that count function. We've got this assumed true value of 30. We can find the sample mean by simply taking the average of this BMI variable, right? So we'll select that BMI variable. We get 29.5 approximately. I think if we extend this, let me see. Let's go. Yeah, all right, it's a little bit off of that, but pretty close to that. For the sake of writing it out, it makes it easier if we have it there. So how can I find my test statistic? Well, this is now I take my sample statistic. Well, now it's my sample mean. I subtract the assumed true statistic or the assumed true mean. And now instead of dividing by the standard deviation of my sample proportions, I divide by the standard deviation of my sample means, which is the square root of my population variance divided by my sample size, right? And I would just get that formula. If I go back to last week's slides, we had that formula. We were using it to do examples by hand. I'm just entering that into Excel here, okay? And just clicking on, where the different things are that I want, okay? That shouldn't be too bad. So once we have this test statistic, right, and I want to do this at a 95% confidence level or an alpha of 0.05, I get this test statistic that's negative, which makes sense because I found a sample mean below what I assume to be true here. Right? Not much below, but it was below it. So now if I want to find a p-value, well, I still get to use that standard normal distribution, so norm.s.dist. But now with a left-tailed test, it's even easier because my p-value, right, was the area to the left. And that's, what Excel will tell me. So I don't have to worry about kind of looking for the area to the right here, subtracting things from 1. So I just tell it my z-value, comma 1. It'll return to me the area to the left of that z-value I selected. Right? So I get a pretty high p-value here. So I should already be kind of thinking I'm not going to be able to reject any of our conventional levels of alpha. Because I can only reject if that p-value is less than an alpha, or alpha, and our alpha here is 0.05. Definitely not less than 0.05, right? That 0.21 is not. I could do the same thing I did before for my rejection decision. So if this p-value is less than my alpha value, right? If that's true, put the word reject. Maybe we won't be so loud this time. And then if it's not true, put the word fail to reject. Okay? So we failed to reject here, which is what we kind of said, looking just at the p-value and alpha. It's definitely not less than our alpha of 0.05. So we get a rejection decision. If we want to do the critical value, well, for a left-tailed test, when we're dealing with critical values, we said our critical values for a left-tailed test should be what? Negative, right? It would be the same values we found for the right-tailed test, but they're negative, right? Because it's the value that gives me alpha in that lower left tail now. So now when I go to Excel and I use that norm.s.inv, I tell it I want alpha in my tail, but because that norm.s.inv is looking at the lower left tail, I only have to tell alpha. That's exactly what I wanted. I wanted that lower left tail for a left tail test. So the left tail tests are really a little bit easier. So I can go here, use that norm.s.inv because I now know the area I want in the tail, which is alpha, right? Hopefully I didn't say it was 0.1. That was the last example, right? We have 0.05 now. But that's the area I want in the left tail, so I don't have to do 1 minus. I don't have to worry about any of that. Okay? So norm.s.inv, and then just select your alpha. That'll give you your critical value for that left tail test. Okay? Sure enough, if I think about this critical value of negative 1.64, and then if I were to plot my test statistic of negative 0.77, so here I found the critical value was about negative 1.64 something. My test statistic, if I plot that, well, that was negative 0.77, not even close to being in that rejection region, right? So I'm going to fail to reject, right? Just like my p-value was pretty high, so I failed to reject there because it wasn't going to be less than alpha. Both lead us to kind of the same decision there. So I could write that if statement again, which I'll do here, just to kind of give you more examples of how we use that. So if that critical value, right? But now with a left tail test, it's a little bit trickier with this if statement because I only reject if my test statistic is in this region, which would actually mean my test statistic would have to be less than my critical value. It was the reverse for a right tail test because we were working with positive numbers instead of negative numbers. And this is why I said last class, what we could do is actually just take the absolute value, and then it would always be if the absolute value of my test statistic is greater than the absolute value of my critical value. But it doesn't matter. You can take the absolute value, or you can draw it out and just remember, oh yeah, I'm only rejecting if my test statistic is over here, which would make it less than my critical value, right? So when we write it out in Excel this time, we'll say if that test statistic is less than my critical value, or a kind of larger negative value, now that's when I will reject. And if it's not, I'll fail to reject, right? Same kind of thing. Okay? So hopefully this gives me the same rejection decision that I had before. Sure enough, it does. Right? And I could play around with alpha here. I don't think because it's it's not going to change anything unless I get to like an alpha of 0.3, which saying things with 70% confidence isn't that as useful as being able to say it with 90 or 95% confidence, right? So we'll leave that at 0.05. And this is how it's very similar, right? These proportion examples and these sample means where we know or we're given the population variance, they're really very similar, right? I could do a right-tailed test for a sample mean, or I could do a left-tailed test, or I could do a two-tailed test. We didn't get an example like that today. But next class, when we are looking at the last type of problems that we have where we don't know the population variance, I'll show you an example of a two-tailed test in Excel. We'll work through a few two-tailed tests by hand as well. Those ones are a little bit trickier. So I just wanted to kind of build up our confidence with these left and right-tailed tests today, okay? So I'll get that next Connect assignment up. It's really just hypothesis testing problems. Like I said, we haven't went over how to do the sample variance ones yet. So if you're starting to look at that assignment, the last questions towards the end might not make as much sense, but All right. I will see you guys on Wednesday.